Hello! In this video, I'm going to prove a result that characterizes which ideals in f of x, a polynomial ring with coefficients from a field, are maximal. In an earlier video, I showed that all of the ideals in f of x are principal. The question is, which principal ideals are maximal? It has something to do with the actual polynomial that is generating the principal ideal. I'm going to call it p of x in this theorem. And we're going to assume that p of x is any non-zero polynomial. It turns out that that principal ideal will be maximal if and only if p of x is irreducible over f. In order to prove this, I have to go both forwards and backwards with my proof. And I'm going to do both directions by contrapositive. So if I want to prove the forward direction, that one of these ideals is maximal, implies that p of x is irreducible, I'm going to start for the forward direction by assuming that p of x is reducible. That it is reducible over capital F. We're going to start that way. This just means that we can factor p of x as a product of two polynomials of lower degree. So I'm going to write p of x is equal to g of x times h of x, where the degree of g of x and the degree of h of x are both less than the degree of p of x. So we don't have just a trivial factorization here, where one of the polynomials is just a unit or something. We have two strictly lower degree polynomials. G of x and h of x are strictly of lower degree, and I'm hopefully now going to convince you that the principal ideal generated by p of x is not maximal. And in fact, my claim will be that we can put another ideal larger than the principal ideal generated by p of x inside of here. And I can actually pick either g of x or h of x to do this with, but I'm going to go ahead and do it like this. So this is my claim, namely that p of x is not maximal, that in other words there is another ideal that we can properly sandwich strictly between the whole ring and the principal ideal in question. There's a lot to be checked here. I first want to note that p of x is certainly a multiple of g of x. We can see that from the boxed equation. P of x is a multiple of g of x. And that means that any multiple of p of x will still be a multiple of g of x. So certainly the first ideal is a subset of the second ideal, which is a subset of the third ideal, for sure. However, I claim that g of x cannot be a multiple of p of x. And that's because of the degree. If g of x was a multiple of p of x, its degree would have to be at least as much as the degree of p of x. So let me just make a note of this here. By degree considerations, p of x, I'm sorry, I should say it the other way around, g of x cannot live in the principal ideal generated by p of x. And that means that its ideal that it generates is strictly larger than the principal ideal generated by p of x. Because there's something here, namely g of x itself, that does not live here. There's something here that does not live here, so we do not have subset going backwards. This is a strict one-way subset relationship. The principal ideal generated by g of x is properly larger than the principal ideal generated by p of x. In other words, it's strictly larger. Great. On the other hand, g of x is not a unit. In fact, its degree, maybe we should have said this over here, the degree of g of x and of h of x has to be at least 1. Because otherwise we have a trivial factorization here. So I'm just simply going to note that, however, I'll make the note this way. 1 is not in the principal ideal generated by g of x. Because g of x is already not a constant. It already has degree at least 1, and so all multiples of it will have degree at least 1. Constants won't be in there, right? Constants won't make it in there. And so that means that the principal ideal generated by g of x is not equal to the whole f of x. So these proper subsets are in fact correct. We have in fact sandwiched an ideal generated by g of x strictly between the ideal that we're now saying is not maximal and the entire polynomial ring f of x. So if p of x is reducible, then our ideal is not maximal, which is what this claim basically shows. Okay, I'll let you pause and reflect on this for a moment. Feel free to do that, and then I will erase and we'll prove the other direction. To prove the reverse implication, I am also going to do this by contrapositive. I'm going to suppose that the principal ideal generated by p of x is not maximal. And I am going to try to show that therefore p of x is reducible, that I can factor it into two smaller polynomials. So if p of x is not a principally maximal ideal, then I know that there's some other ideal that I can sandwich between it and the whole big f of x. But let's remember something. Let's remember that all ideals in f of x are principal. That means that whatever this ideal is that I'm going to put in here should have a polynomial generator. Let's call it h of x again. So this would be for some h of x, an element of capital F of x. And I'm anxious to try to figure out how to factor p of x. Well, the thing is that p of x lives in the principal ideal generated by h of x. In other words, p of x is a multiple of h of x. Let's just say h of x times q of x for some q of x in capital F of x. Okay? And this looks like we are showing that p of x is reducible. The only thing I need to convince you of here is that this is not a trivial factorization. But it's not. H of x is not just a constant, because if h of x was a constant, then these two ideals would be the same. In other words, if h of x was a constant, we would have a unit inside of this principal ideal, and if that was the case, then the ideal would be the whole f of x, right? Anytime there's a unit inside of an ideal, that ideal is the whole big ring, the whole big universe. So h of x is not a unit. Let's write this down. Since the principal ideal generated by h of x is not the whole f of x, h of x is not a unit. It's not a unit. On the other hand, neither is q of x. If q of x was a unit, then we actually could rewrite h of x in terms of p of x, and this first subset equation would be an equal sign, which it's not. Right? I'm going to say also q of x is not a unit. When I say not a unit, I mean not constant. The only units in this scenario would be non-zero constant polynomials. And neither one of these two things is going to be a unit, which means you have not factored this polynomial p of x in a trivial manner. It's a legit reducible expression for p of x. Q of x is not a unit, otherwise h of x would actually live as a multiple of p of x as well. We could just solve for h of x by moving the unit q of x to the other side with the inverse. We would use the inverse to do that. So, in fact, in this case, h of x would therefore create a principal ideal that's contained in p of x. But we already said that p of x is contained in h of x. That would make them equal. And we're not starting off with that premise. We are saying p of x is not maximal so that there is a strictly larger ideal, right, that contains this principal ideal generated by p of x. We don't want to be coming to the conclusion that somehow the p of x and h of x generate the same ideal, which is what we would be saying here. So, what this means is that we have actually factored p of x in an interesting way, not just cheating with units. And so p of x, if we've done that, if we've been able to do that, then p of x is reducible. I hope this makes sense. I encourage you to pause and reflect on everything that's written here. Annotate your notes however you need to try to clarify it for yourself. If there's questions, I hope that you'll ask me about it. Otherwise, thank you so much, everybody, for taking the time to watch this today. And I look forward to seeing you guys all again soon in the next video. Bye for now.